go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it gets me chart title, it gives me all this stuff. Yeah, also, I'll show this again real quick. Got all these options, got so many cool things, it's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everyone, it's time for Office Hours. Who we got in chat right now? Let's boot up Mubot. Let's see if anyone's here. Do some work. Get my Pearson loaded up. It's time for some work. Testing webinar. Okay, Mubot's loaded up. Loading up my Pearson. See if anyone's in the chat. There we go. We're streaming online. Who all is here? No one's here yet. Maybe do a little 320 start. I always do a little 320 in the background. So let me see. Let me message 320 and say, hey, we're streaming. Swing by and check out. Here we go. 20 seconds. Message 320 and say, hey, swing on by. At BS320. Want help with this week's assignment? I am currently streaming. Let's say, here we go. Yeah. Stant 201. Working on assignments. Need help. I am currently streaming. There we go. Messaging people. So easy with Discord to just message people and be like, hey, we're currently streaming. So come check it out. There we go. Let's go here and do a little 320 to start. We'll see if anyone swings by here. And then we can do whatever work they want. So let's go over here, put a note. BS320, checking regression assignment. Let's go over here to the main screen. Okay, so we're talking about checking regression right now. I feel like I'm a little over there. There we go, perfect. So with checking regression, hey, Will, good to see you here. Yeah, I got a second haircut. So I don't know if you're seeing first or second haircut or whatever. And I just got texted by Brad Mondow. Well, kind of, sort of. But not real, just his automated thing. But if you have questions, we'll drop them in the chat. We can get working on them. So with this right here, we're going to talk a little 320, but ask questions away, whatever you're thinking. So here we go, 320. We're talking about regression a little bit. And I'm going to load up the library reg class, which does regression for us. It's called regression class. That's what reg class means. And then we're going to go right here, load up some data just so we can work with it. That's survey 10 data, loads it to the global environment. Now we go here and we save L or save M or save into M in LM. Probably second, but I only got first. I got my first one 9 months. No questions, but I miss having. Oh, thank you, Will, right there with 100 points. Mubot's in the chat right there. But thank you so much, Will. I appreciate that. Height, weight, data equals survey 10 right there. There we go. So what we've done right here is we've created a regression. So I'm going to show a few other things right here, things we don't always use. We need to load up dplyr. We need to go to glimpse. Glimpse is a cool function that gives you a glimpse of the data frame. Hey, Jesse. Hey, Ella. Feel free to ask questions. We're looking at this data frame right now, which is basically an Excel spreadsheet. So when you think about data, it looks like jump right here. The glimpse function is going to allow you to see the variables in the start of it, like female, 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 male, and then you see height, weight, desired weight. You see all the vectors. Gives you some information on them, telling you that this is a factor, which is a categorical variable. Double means it's basically a number, stands for double decimal precision. Integer means it's an integer. So integers are like whole numbers. We talk about continuous or discrete numbers. So integers are discrete, like 1, 2, 3, 4, 5. Double decimal precision basically means it can have decimals right there, which is a continuous variable. So pretty interesting stuff we have going on right there. And we're making a regression. So this is a little bit of review of regression for 201, but ask any questions you have. We're doing regression because we're creating a linear model. So what's really cool in 320 is we can easily make this and visualize it by going to visualize the linear model. And so this is the linear model right here, where we see as people weigh more, they are generally taller. Now, it's not cause and effect. You can't get taller by gaining weight. That's not how this works. but we can make a summary of the model and see the coefficient of the slope right here. Hey, Brandon, good to see you here. Feel free to ask questions. We have chapter 13 coming up. Let's do that next. There's the coefficient of the slope for two individuals who differ by 1 pound, because differ by 1. Good to see you here, Kelsey. Differ by 1 unit of X are expected to differ by blank units of Y. So people who weigh 1 pound more are expected to be about 0.07 inches taller. Someone who weighs 0 pounds would be expected to be 56.34 inches tall. And somebody's weight explains 36.13% of the variation in their height. I guess, and 320, if you swing by, we won't get into this too much because this is breaking away from 201 now. We get into the statistical test to see if the regression is a good regression. But Jesse has a great question right there. So let's go over and do Jesse's question. But you want to, if you're in 320, start doing the check regression. Good old Survey 10, still using it. But interestingly enough, and I'll mention this right before we jump into it, Jesse's got 2 great questions to start us off right there. What we've started doing, check this out, Will. What I've done right here is I've actually changed up all the assignments. So check this out. The assignments now, and I wonder if you know this about this site. Can we do chapter 12? Yeah, I think we did that one yesterday. We'll do it. Hey, Ria, good to see you. How you doing? Let me throw you 100 points. Good to see you here. The assignments now are doing Kaggle data. I got to change this over. I think I can just change this right here. So we're using Kaggle data now. So this is week 8 assignment. I didn't change it to week 8 right there. But they have to use Kaggle data for all their assignments. So they have to go in and load in all their data, running the check regression with quantitative variables. So they're no longer using Survey 10 for the assignments. They have to go in, find data on Kaggle. Yeah, Kaggle's super cool, right? So I made a getting started video right here. There's long hair Brian. Oh my gosh, look how crazy long my hair is. Now I look professional. What have I done to myself? But we were loading in some Titanic data right here, and we talk about how to do it. Crazy longer hair Brian. Now I'm professional Brian again. So what have I done? I think that's is that Capstone? I don't teach Capstone. Brandon, thanks for asking, but I don't teach Capstone. I can't say that I don't teach Capstone. But that's a fun class. Thank you, Jesse, right there. 100 points, Jesse, saying that right there. Feel free to check that out, and we can swing back to that question. Let's go do. Jesse's got some great questions here to start. Okay, let's start it up with those. Jesse, let me throw you another 100 points. Thank you for helping out. We'll try to get to as many questions as we can, as we usually do. But when people help out and they put those links, we can do even more. And we try to mark all. And Jesse, like, I think Jesse's seen, we mark all the videos. So you can always swing back by, check out what was done. And that's really helpful right there. So I found a hotel data set from our Phil's database in 409. And case 4 has hotel data in it. Doesn't tell you. Oh, cool. I found my account. When are you coming to campus? I should be back to campus in the summer. Back for good. Back for 100% back to campus. So that'll be really exciting. Thank you. That makes me nice for everyone to be like, hey, when are you going to be back? The portion of adult women in the United States is approximately. That's a quiz question, right? So let's go do that. The proportion of adult women. Sounds like a good question. Here we go. Yay. Oh, awesome, Ria. Yeah. I'm excited to see everyone and meet everyone. I've met so many students, and it's so crazy. It's like I haven't met my students a lot of times. So it's really nice to get to meet the students. Stat 201, chapter 13 quiz. Are you ever going to? Yeah, we're going to do in person next semester in the fall. Chapter 13 quiz, the proportion of adult women. I'll be back teaching in person. Oh my gosh. What has the world come to? Brian will be teaching in person on campus. I'll be doing like 320 in person. And I think I'm going to drive my students crazy because I'm going to have a lot of requirements to be in class, to be there. I'm graduating. No, swing on by. My Pearson's being really weird. It's not loading. Like it's... So I'll be teaching 201, 320. Am I teaching 474? Oh my gosh. Hopefully I don't have 3 preps. I like teaching 474, but teaching 3 preps is really tough. Because then you've got like 201, 320, and 474, and everything's like floating around. I know it's like, I take, you take like 4 or 5 courses, but it's different being like the organizer, runner of a course, and the person in charge of getting everything going. I'm in 474, no idea what capstone is. Like that. What is going on? My Pearson, what are you doing? Let's try reloading a question. It's just hanging right here. Is anyone else having problems with my Pearson? Maybe that's what the message was. No, totally different thing. What is going on? Sometimes there's problems with my Pearson. See, I'm trying to load it. I'm trying to load the quiz right there. Might need to turn on some air. Getting a little hot. Trying to wrap my head around the KFold cross-validation at the moment. So with KFold cross-validation, basically you're dividing your data set up into 4 separate parts. I'll talk about that just briefly here as we try to get that going. Put our answers in a percent. Yeah, let me know. I get points back for stuff like that. So usually you just make your model from all the data, right? Yours isn't working either? Oh, gosh. If you tell me how the question goes, it probably has you find the mean and the standard deviation of the distribution. I kind of know a lot from memory. I can kind of do the question a little bit. Hopefully, sometimes it has a bug for like a minute or two, and then it gets fixed up. See you, Ria. I'll see you next semester. That'd be awesome. So with this right here, are you able to fix them if we start a new attempt? Yeah. You just do multiple attempts, and then I can fix a previous attempt. KFold cross-validation. The K in KFold stands for how many folds you are making. This is KFold what? And then we'll try my Pearson again in a moment. This is KFold what? How many folds are there in this data now? Like if you had 1,000 observations, so n equals 1,000. This is KFold cross-validation. So n equals 1,000 right here. How many folds are there in the data? Now, be careful. You might think like you're folding a piece of paper or something, but folds is like how many bins are there? How many groups are there? So don't look at the lines and think of those as the folds. The folds are how many groups there are, like how many segments of the data there are. There's 4, Brandon, you got it right there. So this is KFold 4 cross-validation. So the way the process works is this. You make the model on all but one fold, and it's called KFold cross-validation because one of the folds validates the model. So I guess let me rename this right here, and then we'll try my Pearson again in a moment, and I'll just talk about KFold cross-validation in this section. So BAS 474, KFold cross-validation. Okay, so you make the model on, good to see you here, Robert. You make the model on all but one of the folds, and then you validate it on the last remaining fold over there. So the way this would look in theory is if you have your data, you would go right here and you would go, let me think how it would work. Mine is working now. Oh, I just had to re-enter it. Cool. Then I'll finish this up here and then we'll go back over to that. So you would take your 1,000 observations, you would randomly put them into these groups. And the first time you make the model, you're making it on 750 and validating it here. And you're seeing if the model works and makes good predictions on the validation portion. And that's going to be your RMSE validation, the typical miss it makes on the validation subset. But the reason it's the KFold cross-validation process is because you then repeat the process, but you switch where the validation portion is, such that the validation portion becomes the 3rd fold of the data. So you make it from the 3 other folds and validate it on that fold. And when you do this, how many RMSE validations will you get? So if you repeat this process over the 4 folds, how many RMSE validations will you get? And we'll finish this up here in a second. How many RMSE? Because you're going to do this 4 times. So you're going to get 4 RMSEs, which are typical misses the model makes. And so when you get 4 RMSEs, then you could take the average. And not only could you take the average of these, which this goes to 201 now, you could also get the what else. So you could get the average of them and also the what of them, which I guess would be more like a Y bar at this point, which is notation for our class. You could get the Y bar, which is the average of those. You could also get the what of the RMSE, because they're not all going to be the same. So you could find the average of them, which is kind of on average what the typical miss is across when you make different models with different subsets of data. So you can get the average typical miss, and you can also get the standard deviation, which is the variation. Since they're not all the same, there'll be variation in your typical miss. And then you can look at like sometimes a little bit higher, sometimes a little bit lower. So how does this model typically work? And then what's the variation in it? So this lets us understand, like, given different subsets of data, which is what we're doing over here with the KFold cross-validation process, because the third time it runs, it'll move the validation portion here, make it on those 3 subsets of data, validate it on the second, and then the fourth time it runs, it'll make it, or it'll validate on the first portion, and then it'll make it on the other 3 portions. So it's always validating the model on what it does on the 3 folds, if it's doing KFold 4, to see if it works. And then we can find out how much does it typically miss by when it makes a model and what the variation in the typical miss is. Going back. Well, it is time for some 201. That's a little bit on KFold cross-validation process, and it's all automated for us, so we're good to go on that. Okay. It looks like it's loading. No! So what did you say, Jesse? Jesse said, mine is working. I just had to leave and re-enter. Let me try reloading my Pearson completely. Like, let me just try like exiting out of my Pearson 100%. It's so weird. Like, I swear the first like 5 years I used my Pearson, it had no problems. No problems for the longest time. Everything's loading on the main pages. There we go. Literally, Jesse said it. Just had to leave and come back in. No worries. I'll do these right here, Jesse, and hopefully we got someone to like work along with. But I'll do these right here. The proportion of adult women. So we'll try to find all the questions right here. And the proportion of adult women. I thought that was the first one. Here we go. The proportion of adult women. Stat 201. Chapter 13 quiz. The proportion of adult women. Okay. Let's check this out. The proportion of adult women. Here we go. The proportion of adult women in the United States is approximately 51%. A marketing survey telephones 470 people at random. Complete the following parts. So a lot of these questions boil down to notation. You have to know the notation. Please pull out your notebook right now and write down, as I do this, the notation for this problem. For 100 points, does anyone know any of the notation in this problem right here? Does anyone know, and good job, Brandon, right there, I like that. Does anyone know how they think of this stuff? What is any of the notation in this problem? Like, what is 51% and what is 470? If you know the notation, this problem becomes a lot easier because it says the proportion. Hey, Maisie, good to see you here. What is any of the notation for 100 points right here? So it says the proportion of adult women in the United States is approximately, it should just say is this. So it should say the proportion of adult women in the United States is 51%. They survey 470 people. So what is the notation? And that's the key to this question. Once you have the notation, this question becomes a lot easier. This question becomes like, boom, done with it. But if you don't know the notation, this problem is like, what in the world are we doing? Because this is the chapter. Great job, Brandon, right there. Automatically, class is not over. Brandon got us 100 points right there. N equals 470. And so there we go. Hey, McKenna, good to see you here. So feel free to drop in that notation right here. And we're just practicing or ask questions on what you're stuck on. We have here P is the true proportion. And Q is the complement. That's 1 minus P right there. So they should add up to 1 right there. Hey, Cassidy, good to see you here. Drop questions if you got them. Jesse had a few, so we're going to work on those. And so with this, we now are going to be asked things like, what is the mean for the distribution of the sample proportion? That's not something you multiply to find. It stands for the mean of the distribution of the sample proportion. It's a whole idea of my old points. Nice job right there. And then that is equal to P. You know what's interesting? We already know that answer. And then we want the standard deviation for the distribution of the sample proportion. And that is equal to P times Q over N square root. P times Q over N square root. And so this one we already have solved. This one we're going to have to plug in the numbers. And there we go. So what does that equal? Brandon, good to see you. Well, Brandon's been here. and 0.023. There we go. And so that is the standard deviation or the variation for the distribution of the sample proportion. Like we were just working on a second ago, Brandon, this is the mean and the standard deviation. So it's what we expect and then the variation around that. So let's go ahead and look at the problem, and it's what it's asking for. It says, what proportion of the sample would you expect to be women? And that's the mean of the distribution. If 51% of the United States is women, then we would expect 51% of our sample to be women. Doesn't mean it will be that, but that's what we would expect. The standard deviation is the formula we just solved to 3 decimals. We got it right there. How many women on average would you expect? So this is actually checking the third condition right here. The third condition, do I still have those notes open? I think I do right here, is the success failure condition, which is the expected amount of successes. So these are the 3 conditions for the distribution of the sample proportion to be normally distributed. We need to randomly select people. We need to select less than 10%. That's usually confusing to people. Less than 10% of the population. And then last but not least, we pause and we check the variable type. That's not a condition. It's just what we do to make sure we do the right third condition. And the third condition for categorical data is success failure. So the third condition here is going to be we need at least 10 successes expected in this instance, because we are saying if the truth is this is how many we would expect. So the formula is going to be n times p for the amount of expected successes and n times q for the amount of expected failures. So we can check the third condition right here. We know n is equal to 470. We know p is equal to 51. And think about this. If we sampled, let's say, 100 Americans, how many would you expect to be women? So just think about what this formula is finding for you. Like, think theoretically, like if you sampled 100 Americans and it's true that 51% of Americans are women, then, is that right grammar? Maybe. Then how many would you expect to be women if we sampled 100? So think about what the formula is finding. It's not finding how many you did find. It's saying, well, how many would I expect? How many would you expect? If 51% of Americans are women, then we sample 100 people. How many women would you expect in your sample? How many women would you expect? No, McKenna, I totally forgot about that code right there. So if 51% of Americans are women and we sample 100, well, then we'd expect, we can just multiply these together, and that'd be 51 women. But what if we sampled 200 Americans? If we sampled 200 Americans, well, you're still just multiplying them, and you'd expect 102. So when we do this formula right here and we multiply these values by each other, p and n times each other, then we are going to find out the expected value of how many women we would expect to see. Nice, McKenna. There we go. So, and it's weird, it's a decimal, but usually ignore that because it means on average over repeated trials. It's not in one instance. It might even say round to the nearest whole number as needed. So 240, and that should do it. Really good question right there. Understanding the theory is probably the most important parts of it. We got quite a few more. I think Jesse had like 2 more. Let me double check Jesse's questions right here. We did the proportion of adult women. We have an automatic character recognition device. An automatic character recognition device. Wow. Apparently I know where these are at. So an automatic character recognition device here at 24. Chapter 13 quiz. An automatic character recognition device. Okay, an automatic character recognition device successfully reads something about 85% of the time. So we need to identify what that is. To estimate what would happen, they do a bunch of simulations right here with certain sample sizes. So when you get a question like this, immediately notice the notation in it. So what they're getting at right here is the proportion of times something is read correctly. So we go right here, and this is the true proportion it reads correctly. And the proportion of times it doesn't read correctly is 15%. So then we do it with different sample sizes down here. And one thing you'll notice is for a very small sample size, we do not pass the success failure condition, which says we need at least 10 successes, at least 10 failures. So if we do it for the sample size of 20, you'd get 20 times 0.85, which is 17. You can actually solve for the remaining one because these will add up to 20. And you can see right here, we do not have at least 10 successes down there when we do 20 times 0.15, which is the amount of times it doesn't read it correctly. It looks like we will probably reach the amount of required successes when we get to, or failures in this instance, because we need at least 10 successes, at least 10 failures. I think we reach it with 75. That's a close call, right? 75. Yes, we do. So we have it when we reach 75 when you check the amount of successes and the amount of failures. So this one right here gets a little bit specific on it, looking at the histograms. Oof. So let's see if they follow what I say. So there's the data. And if you notice, the mean is about at the mean. The theoretical mean is always 85 because that is what we solved a moment ago, that the mean for the distribution of the sample proportion is equal to the mean. So if we write it out for this problem, we have our notation for this problem. And we know that mu p hat is equal to p, which is equal to 0.85. And they did a simulation, which is going to kind of mimic reality. And then the standard deviation is going to get smaller. And this is something they probably want you to see in this, because when you do this, it's p times q over n square root. And take a look up here that the n is increasing. So if n gets bigger, the standard deviation quantity will get smaller as n gets bigger. So that's kind of the theory right there that I think they're going to allude to in this problem. And looking at the histograms is really going to illustrate this. We could look at the data right there, but notice how it becomes a lot tighter between 0.7 to 0.9, where at the small sample size is between 0.5 and 1. Now, the other thing to note also is it's left skewed to begin with, because we don't meet the conditions for it to be nearly normal, we should say, just normally distributed, approximately normal. And the better we meet the conditions, the more normal it is. And the big problem we had, as we illustrated, was the success failure condition. At these small sample sizes, there's not at least 10 successes, at least 10 failures. Once again, times 0.85 times 20 to find the amount of successes, and 0.15 times 20 to find the amount of expected failures, given the truth. 75 is where it seems to be approximately normal. 50 looks close-ish, but we did the math on it. They might say it's 50, but 50 does not have at least 10 successes. So I'm going to go with 75. Hopefully they give it to us based on the success failure condition. Oh, here it is. What does the success failure condition say about what sample size should be used? The values of NP and NQ are both at least 10, so success failure condition is met. Well, that's true, right? The values of NP are at least 10, and the values of NQ is... No. So we need both to be at least 10. And I think... So wait. Stop it. There we go. So really, this question only boiled down to checking the success failure condition. A lot of interesting stuff right here with the different sample sizes, but what they really wanted you to do to know that this is met, which I was thinking is why we know our theory, is you want to take all those different n's and try out something like 20 times 0.85, which is 1 of the n times p, and that is equal to 17. That's at least 10 successes expected, and 20 times 0.15, which is n times q, which is going to be equal to 3, which is not at least 10 successes. So since you do not have at least 10 successes and at least 10 failures, you would not meet it there. When you plug in 50, that's just going to be half of those. So half of those is, there we go, 42.5 and 7.5 when you multiply them out. So it's not met right there. And then we need half of, well, not half of this. Oof. Harder to do this math on this one. So now 75 can be a half of a half. So I won't do it in my head. There's the answer right there, 11.25. And that's where you meet it. You have at least 10 successes. And then up here at the top one, we can subtract off of this to get 63.75. And you have at least 10 expected successes there. The bottom one's the expected failures. And you can check your math, but they do have to add up to 75 when you add these up, because this is the amount of expected successes out of 75, and this is the amount of expected failures. Since we have at least 10 successes, at least 10 expected failures, then we see that it is basically normal right here. This one looks kind of normal, but bins can be deceptive. We don't have at least 10 successes and at least 10 failures. So I think they're trying to trick you by showing this. This is obviously wrong. This is obviously good. Then you might be like, which of these two is correct? But the bottom question alludes to meeting the success failure condition. And since you have at least 10 expected successes and at least 10 expected failures, you're good to go. Ask more questions. We'll do another one right here. This one was a really good review of the success failure condition, knowing how to solve it. Make sure to know your notation, that this is the true proportion and this is the complement of the true proportion. And then we tried it with different sample sizes to see what was theoretically possible. Suppose 30% of people in your hometown. Suppose 30% of people. Oh, another character recognition one. Suppose 30% of people in your hometown. Ooh, it's a short one. Back when I was in your 201 class, you and your other kind of paper about an online teaching. Yeah, let me drop that right here. Thank you, Brandon. Yeah, we did. World of Edcraft. Harvard. Here it is right here with MIT. So it was published by Harvard Data Science Review. So here it is for Harvard Data Science Review. We'll mention that and then we'll go over to the other one. Wow, glad you remember that. So here it is, World of Edcraft. So here is the publication. It's got videos and everything in it. There's Dr. Sean Willems. There's Dr. Andrew Lowe. Amazing guy. There's me, Brian Stevens, with my long hair. It's a different shirt. That's a V-neck shirt. If you can't see it, it's a V-neck shirt. Dr. Andrew Lowe teaching. There's my home setup right there. But no, it got well, they're asking. Thank you, Brandon, right there for asking. A lot of other people doing what we're doing also. Here's the other paper right here. Well, this is the original copy of the paper, last revised last year, and you can download, open the PDF. So there's the download, and then here's the World of Edcraft paper. Check it out, really cool paper right there. And then huge thank you to Dr. Andrew Lowe. Really cool that we got this. So here's my Google profile now, and of course I've clicked my links, but I need to get something published this year, right? Last year, 3, it's kind of crazy, but my wife also published her work. So if you ever took 320, this is my wife's work right here. Well, and I did the statistics for it. So in the AVMA journal, the American Veterinary Medical Association journal. There I am, Brian J. Stevens right there. Specs of your monster PC, nice. The 2080 Ti. And then if you go down here, you can see some of our awesome graphics created inside of R. So this is a ggplot right here showing the differences. And you can actually see at the heart rate differences in the Quaker parrots at different times right there. And then we've got other graphics right here showing the time plot. This is a time plot right here of 2 different series. And then we've got different statistical significance measures between, whether it was different at that time, whether it was different from baseline. The star means different from baseline right there. And the little cross right there, I think, means difference between the treatments. So kind of seeing what was going on. Oh, the coolest graphic we had was this one, which was the presence and absence of tremors at the high dose, or the HDA, which is the high dose, I believe, and the low dose. And so you can see here, especially just by the amount of dots, that there were a lot more tremors at the higher dose for the parrots. And they monitored them over a certain amount of time. This is all made in R. Every one of these graphics was made in R. I still have all the work for it. So I still have all my work. So here we go. This is the code right here that makes the graphics. So this is all the code we wrote right here. I think it'll all still load. Every once in a while I forget one little thing. Oh my God, read Excel. Look at that. I forgot to put a library because I probably loaded up. Read Excel. There we go. Now rerun it. There we go. We made many iterations. Could not find theme. GG themes. Ay. Put all your stuff in the same thing. There we go. Now it's making all the different ones, and there you go. Easy center title. We went through many different iterations, different ideas, and this might not have one of the final ones. So there we go. This is one of the final ones you just saw right there. There it is. There's one of the final graphics. That's one of the graphics. Went through many different iterations of possibilities of like what it could look like, and tried to find different ways of doing it with different just analysis. Could not find easy center title. Oh my gosh. What am I doing? My library GG easy. I had so many files open when we were working on this. So I was like working on like 50 different things. It was interesting because I would come up with different ideas and then we would send it off and they'd be like, well, we like this. We don't like this. Could you change this? This doesn't look so good. We'd prefer it look like this. Like this right here was one idea. I did like a mosaic plot idea. Yeah, well, the problem is if you keep all the libraries loaded in, then it will take longer to load up. So if you were to load all your libraries at one point, like if you load up all your libraries, it's going to take a long time to load them. And so this was, there we go. This was too much. It was hard to, there we go. This was one idea I had, but I think Chelsea didn't like that the bars were down there because that was like 0 for the groups. It's also a little bit hard to see the differences. So this was what I thought might be best for showing the difference between the treatments. So that was one idea, and then we settled on this idea instead right here with the side-by-side bar charts. So they seem to like this a lot better, showing it's a little bit easier to see the decrease in the count of birds in that group. It's also a little bit easier to see the ordered. So we did like side-by-side bar charts across different groups on a time series, with the baseline being down here in the same x-axis. So you look at this, a lot of scaling of axis. Yeah, exactly. And that's the goal right there, is to show both. And this is a facet grid inside of R. So we try to make data look as best as we can possibly make it. She didn't want any titles. That was a big thing. She was like, no, we're not going to add titles to these. Like, because the title's over here, figure 5. So it doesn't have like a title up top. And then it's got the description of what's going on. And then I ran all the statistics. But yeah, so shouts to my wife right there doing amazing work. And then Sonal did work a long time ago. Oh, did I remove? This is the work Sonal did. Yep. And this one has so many people on it. I'm like one of the last authors right there, but I helped one of my, trying to think what she did this for. I think this was like a Chancellor Scholar thing. I'm trying to remember what it was on. I mean, there it is right there, but I'm trying to remember what it was for. But Sonal right there, really amazing students. Shout out to her. The first publication I had right there, and there I am, like second to last author. But anyways, fun stuff, and you really get to do a lot of cool work and help students, and yeah. But Sonal was top tier, and so honored to work with so many amazing students who I didn't know she was gonna. I've had other students publish stuff too, but she was like, "You're gonna be one of the authors." And I was like, "Hey, that's fine by me. I'll help out." I mean, I'll help out either which way. I've helped out hundreds of students probably at this point. Maybe, yeah, probably hundreds. Like, maybe not published work. I've had a few who've published, but she was like, "You're gonna be on it too," and I was like, "That's good. Hey, fine by me." Get my Google Scholar going. Like it. Okay. Let's check out this next question. Thank you, Brandon, right there. I like talking about that kind of stuff. It's fun. Stat 201, chapter 13, quiz. Yeah, you never know. Yeah, just ask away. Suppose 30% of the people. Okay, let's check this out. Good to see you, Alexandria. And Robert, could you do a nervous kicker? Yeah, let's do nervous kicker next. Suppose 30% of the people in your hometown on their cell phones talk on their cell phones and drive at the same time. Well, that's not bad, my Pearson. It depends. Do you have a hands-free device? So there's nothing, in my opinion, wrong if you press a button. Like, a lot of times I'll just like be at a light and I'll hold down the button. I'll say, call so-and-so. Like, that's as much as turning a radio dial. Like, I mean, you shouldn't be constantly messing with your radio dial, but I literally can just grab my phone, not look at it, hold down the button and say, like, call my brother or something like that. So don't be looking at your phone, punching on it. That's a different thing. But hands-free device over your speakers and stuff, then you're just talking to someone in your car, basically. If you stood on a busy street and watched 50 people drive by, what is the standard deviation of the model you use? So this one is one. Hey, Jesse, good to see you. We're working on this question. It wants the standard deviation. So we got a famous quote for this. Quote 191, P times Q over N square root. P times Q over N square root. So what do you think we're going to have to figure out for this problem? To solve this problem, we're going to have to figure out what? It's so funny. There's only one logical answer. There was only one logical answer. We could maybe not find the answer if we don't have all the information. So I guess there's two answers if you're like, well, do we not have all the answers? The standard deviation of the distribution is the amount of variation in the proportion. So variation in a proportion has to be a decimal variation because proportions are decimals. This is the mean, and they almost give you everything. We could show it by actually showing everything right here because they pretty much give you all the notation. So here's the answers. It said you're going to watch 50 cars go by. So 50 is what? You just have to type in one letter right here. It said you are going to watch 50 cars go by. That is your what? So the problem said you're going to watch 50 cars go by. So what is 50? Very important to know the notation. You're going to watch 50 cars go by. 50 is your what? 50 would be your what? Very important to know your notation. No one's saying the answer yet. 50 is n. Sample size. You're going to take a sample of 50. Now, it is true, or research says that 30% of people are on their cell phone. That makes this P. So if that is P, then we instantly know Q that 70% of people are not. So P and Q add up to 1. So we know P, we know Q right there. P is right there. Exactly. So P is 0.3. That's the truth. And then we have the sample size. So the standard deviation of the sample proportion, this is just a quantity we're going to find. You might as well just call this X. It's not X, but a lot of people think you're multiplying these. You're not multiplying those. That's an idea right there, a full idea. That stands for the standard deviation of the sample proportion, which is variation in what we might see when we take a sample. It's not a multiply thing. It's just one whole concept. So you could just literally call this, we're solving for X. So when we solve for this quantity, it's not actually X. It's just one thing we're solving for, though. The value is P times Q over N square root. And square root of the whole thing, not N square root. It's quantity square root right there. Yeah, no worries, Brandon. That's the key to these problems right here, is knowing the notation. And then you just plug in the values. You just plug in 0.3 times 0.7 over 50. There you go. And so with this right here, there you go. And as I said, there was only one logical value right there, other than maybe we don't have enough information, because we know what the sample size is, we know what the true proportion is, we know what the complement of the true proportion is. This stands for the proportion of people we expect to be on their cell phone, the proportion of people we expect to not be on their cell phone, the sample size we're taking, and then the standard deviation of the sample proportion is this right here. This value of 0.30 is also the expected mean, or on average what we should see. And that's it right there. So just key to know your notation, and then you can solve the problem right there. That's got it. Really good question. Jesse, drop the other ones. I'll show you what we've done real quick. You might be just here for a moment, though. But here's what we've done so far. And we're going to do Chapter 12, a nervous kicker right now. So let's do a nervous kicker from Chapter 12. Chapter 12, a nervous kicker. Nervous kicker. I think it's towards the middle. Nervous kicker. Okay. So this one is interesting right here because it throws you for a loop. Okay, let's check out a nervous kicker. Here we go. So a nervous kicker usually makes about 63% of his first field goal attempts. If he makes his first attempt, his success rate rises to 94%. What is the probability he makes his first two kicks? So Gallup poll, you got it. So think about this one. He has to make his first and then make his second. So what would be the probability he makes his first and then makes his second? What is the probability he makes his first and then makes his second? Probably makes his first 2 kicks. So when we write this out, the math for it is, and you have to watch out because they're throwing you for a little bit of a trick right here. So the probability is makes first and makes second. So what is going to be the mathematics right here? The probability he makes his first and makes his second. Because this one has a sort of conditional probability on it. The probability he makes his first and then makes his second. And if you're wondering, the and right here means multiply. Now you might be saying, doesn't the probability of the second depend on the first? It does. So they are not independent, but it's telling you what the probability is. Jesse, what is? You got it. So it's telling you what the probability is, and it's telling you the new probability, which is not the same as the old one. So we can just multiply. Good to see you, Samuel. And so we can multiply the 2, even though it doesn't meet the rule of independence, because it tells us the new probability. It's saying, here is the new probability given he makes the first kick. So given he makes the first kick, his probability will increase. And there's the new probability. Yep, you just multiply them. Yep. It's tricky because you're like, well, wait a minute, that doesn't meet the rule of independence. But it's telling you there's a new probability. So you can't just do 0.63 times 0.63 because the probability of his second kick depends on his first kick. Does that make sense? So if it was independent, if each kick was independent, the mathematics would just be 0.63 times 0.63. If they were independent, the probability of making 2 kicks, if each kick is independent, would be the probability of making a kick times the probability of making a kick. But the second kick's probability depends on the first kick. Yeah, and then just remember that this is telling you that it actually doesn't meet the rule of independence, that his probability actually increases for the second kick. So you can't just do 0.63 times 0.63. Yep. Sometimes it's like understanding the key parts of the problem is like the whole goal of it to be like, okay, so this is checking the rule of independence. It doesn't meet it. So we can't do 0.63 times 0.63 because his probability actually increases. And it just tells us that here's the probability he makes the first. Here's the probability he makes the second. If he makes the first, then what's the probability he'll make the second next? So makes the first and makes the second. We have the probabilities and we know what they are. Hey, a Gallup poll. And ask more questions. Keep them coming. We'll just keep going through the questions right here. Thank you so much, everyone, for asking. We got a lot of work to do. It's getting warm in Texas again. What temperature is it today? 81. What? It's so hot. First summer I was here in Texas, my studio got so warm. It was like I was like sweating in the studio. No fun. Craziness. 50? Oh man. Lucky Knoxville. Well, you guys had some real cold. Gallup poll. Gallup survey. Is it on the homework or the quiz? Is it part 2? Is it part 2, Jesse? Is it like the mean ones? Because I don't see the Gallup stuff. It's on the quiz? Maybe this one changes. Gallup regularly conducts a poll. Did I preview it? Make sure I think I might have previewed it. Let me check. I might have previewed it, which is the problem. You don't want to preview it when I go to replace questions. No, there's only 10 questions. Quiz 13? What is this? Is it the second quiz 13? Oh, what in the world? What in the world? Well, I was looking at the wrong thing, apparently. Okay, ooh, this one is a tough one. This one is a very tough one, which I'm debating removing right now, because it kind of gets into a little bit of shady territory. Let me mark this one right here. Definitely not one of my favorite questions. I always point that out when I have a not favorite question, but I'm going to try to rope it into what we have. It's definitely one of those questions where I'm like, I don't know about this one. Chapter 13 quiz. Gallup regularly conducts. Also, they go into way too many details on all of these things. So a lot of times when I have problems with the question, it's like Gallup conducts a poll using a Cantrelli scale, which asks people to imagine a ladder with 10 rungs. 0 represents the possible life, worst possible life, and 10 represents the best. Respondents are asked which rung they're on. Thriving, standing on 7 or higher, and expected to be on rung 8 5 years from now. So what they're trying to point out right here is thriving is a category. So we're probably going to look at the proportion of people thriving or suffering. Suffering is on 4 and expected to be on 4 or lower 5 years from now, and struggling. In May 2020, Gallup found that the index had reached the lowest level since the Great Recession of 2008 at 48.82% thriving. So this is a category right here, percent of people in a category with a sample size. So this is what they found in their survey with this sample size. Explain the meaning of p hat in this context. So this is a notation problem right now. P hat is the what. Don't even read their answers. Don't read their answers. P hat is just the what. Something. Don't read their answers. I'm going to pull up the notes right here. P hat is just the what. P hat is just the what. Oh, I need to go to chapter. Is it in this chapter? What's in this chapter right here? P hat is just the what. Notation. This part of the problem's not bad. I think it's the second part where I'm like, P hat is just the sample proportion. So P hat is the sample proportion. So it'd be the percent or proportion of successes, which is the proportion of people not quite predicted. It'll be from the sample. Predicted is what we would get down here usually, which is P is the expected or kind of predicted or truth. So the sample is what we see when we look at the data from a sample size. So they probably, I think they said they had like 20,000 people or something. And so if they had 20,000 people and they got like 47%, we could take 20,000. We're just doing theoretical right here. And that's about how many successes they had or people who were suffering. Does that make sense right here? This is how you would say there were this many people suffering. I think it was suffering or thriving. I think it was thriving, they said, actually. This is how many people were thriving, which is what they're interested in measuring out of their sample size. So this is the sample proportion of people who were thriving. Did they say predicted? Did they use the predicted word? Let's see here. Okay, explain the meaning of P hat is this. Is that 40.82% of these people in the sample, good stuff right there, were classified as thriving. This is the researcher's best estimate of no. This is what P hat is. So that's an error right there. P hat is an estimate of what? P hat would be used as an estimate of what? P hat is an estimate of what? P hat is our estimate of what? So P hat is our estimate because it comes from a sample. P hat is an estimate of what? It's on the screen. P hat is an estimate of what? The true proportion, exactly. So you would guess that the true proportion is probably near this. So we guessed about 47% or something. So the true proportion is probably kind of close to P hat, maybe. So let's see here. I think this one's going to be the best. The meaning of P hat is that 48.82% of the 20,000 people in the sample were classified as thriving. This is the researcher's best estimate of the truth. That's what true proportion is right there. The proportion of all people in this particular geographic area. So that's correct right there. Now it says to calculate the standard error. Now this is a trick, and a lot of times help me solve this will help you solve this. So you have an estimate of the truth right now. And so the standard error is an estimate of the standard deviation. So if you do not know, let me ask you this. If you do not know P, then what do you think you should use? We'll grab this right here. If you do not know P, which rarely do you not know it, well, in these problems, when you're dealing with the truth, funny enough, rarely do you know it. But if you are trying to solve the formula, P times Q over N square root, and you're trying to find the standard deviation of P hat, and you do not know P, what could you use instead to estimate and get a standard error, which is comes from a sample now? The standard error is going to have a small difference in the formula. If you don't know P, which we don't know P right now, we don't know the truth, what could we use instead of P? Like, what would be very similar to use instead of P in this formula? What could we use instead in this formula? And this is the hardest part of this problem, probably. So we don't know what P is. So what would be kind of a good alternative? Instead of using P, it's like, well, let's just use this instead. And then it becomes the standard error. It's no longer a standard deviation. We would call it the standard error. So instead of using P right here, let's not use P because we don't know it. If we don't know P, we should probably use what? And that's no longer called the standard deviation. It's called the standard error. Be hot. And we know that quantity. There's P hat. How am I getting Q hat? Yeah, Moira, good to see her. Moira, 100 points right there. How did I get Q hat? This is probably one of the toughest problems, Moira, because it's a big theory problem. I don't think we've ever put a question on the test like this. How did I get Q hat? Q hat is 1 minus P hat. So you go 1 minus P hat. And there's Q hat right there. So now we plug in the numbers. Yep, great job right there. And we're just going to plug in the numbers. And then what's the sample size? There we go. Square root. There we go. Be very careful on the multiplication there. Say 7 decimals. Oh my gosh. 2, 3, 4, 5, 6, 7. There we go. Oof. Let me divide it up. That's 4. That's 3. We're good. 7 decimals. Be very careful. Explain what the standard error means in this context. The standard error is the best estimate of the standard deviation. That sounds about right. We're going to have 2 similar ones, right? Let me see what this says. The standard error is the best estimate of the standard deviation of the sampling distribution of the proportions, which measures the amount of variation in the sample proportion expected to be seen from samples to sample of this. That sounds correct. The standard error is the best estimate of the margin of error. No. The standard error is the best estimate of the margin. No. The standard error is the best estimate of the standard deviation of the sample distribution standard proportion, which measures the amount of variation in the sample population proportions. No, that's just kind of nonsense at the end. Someone didn't even know how to finish that sentence. There we go. Good. That's exactly what the standard error is. It's an estimate of the standard deviation of the sample proportion because we do not know P, so we had to use P hat instead. So we would want to work this formula, but since we don't know P, we are estimating what the standard deviation is with the standard error. So this is a big theory question right here. It's also knowing your notation that this is P hat and this is N. And then from there, we can solve the question. But really, it's just like, here's P hat, find Q hat. Here's the sample size. Know that we could make an estimate of it. And that's kind of the hardest part of the problem, is that this formula right here is just us estimating. And I think a lot of times to help me solve this, we'll show you those things. Isn't there a help? Do I not get help me solve this? Did we turn off those things? I don't know if we did or not. Gallup regularly conducts an automatic character recognition device. I think we did that one, Savannah. Yep. We just did that one a little while ago. We're going to keep going along right here. We could go back to it. The automatic character recognition one is right over there at 24 minutes in. So check that out, but we can swing back by. I think we got a few other ones. For her final project, Stacy plans on surveying a random sample. For her final project. Let's go find that. I must have not been on the full thing. We didn't do that automatic character reader, so we can do that one next. Is everyone? Yeah, Savannah, 100 points. Thank you for pointing that out. Yep, let's do that other one next. Both of these for her final project. Okay. 101, 53, Stat 201, Chapter 13 quiz for her final project. Okay. Let's do it. For our final project, Stacy plans on serving a random sample of 30 students. There's your sample size right there. On whether or not they plan to go to Florida for spring break. So that's, will you go to Florida? Will you not go to Florida? From past years, she guesses about 14%. What is she trying to guess right there? You're welcome, Savannah. We got it next. What is she trying to guess right here with this 14%? What is she trying to guess right here with this 14%? She's trying to guess what? And that's the key to this problem. With that 14%, she's trying to guess what? What is she trying to guess at? She is taking a guess at the what? Oh, wow. That's funny. What is she trying to guess at with this 14%? That's the key to the problem. So she is taking a sample of 30 students. And she is taking a guess at the what right now? Yep, that's P. Now, what conditions do we have here? We have the three conditions, and you see random. And do you think 30 students is less than 10% of the students at her university? So she did randomly sample the students. So we meet random. Do you think 30 students, her sample size of 30, is less than 10% of all the university students at her university? Is that logical to conclude that 30 students, a sample size of n equals 30, is less than 10%? Yep, definitely. It seems, unless she goes a tiny, I mean, it would have to be very, very tiny. But last but not least, we need to now do, we said that P is equal to something like 15%. So when you do N times P, you get 4.5, which is the expected amount of successes, because this is 30 times 0.15 right there. The amount of expected failures, which is just the people who don't go to Florida, apparently that's a failure now, is 25.5 found by NQ, which NQ is going to be 30 times 0.85 right there. And so that is what we have right there for the values. And when we look at this, it's very important to understand why we fail. If we do not meet the success failure condition, so let's put 30 here and 15, the distribution will not be normal. And this is kind of normal-ish. Kind of normal, but notice here that when you have less expected successes, it's less normal. The more expected successes you get, the more normal it gets. So eventually we reach a point here where it gets very much normal, and we'd want at least 10 successes, at least 10 failures. Now there's 9 expected successes, and we go right here where there's 15 expected successes and it's normal. At this point, we don't have at least 10 expected successes and has a little bit of a right skew to it. And that is found just right here by calculating at least NP greater than or equal to 10, which we do not pass right there, and NQ, and we have the mathematics down here to show sample size times NP and NQ. So we do not meet the success failure condition, and these are needed to check to see if the distribution will be normal. So that's how we would say this doesn't meet it. And it's weird. They give you a bunch of things to check, but no, it does not meet the success failure condition. They break apart randomization right here. We don't need quantitative data. Nearly normal is for quantitative data. So these two just flat out don't apply. It is less than 10%. She didn't meet all the conditions. It was random. And that's got that one right there. Okay, the automatic card reader one. Here we go, automatic reader. Thank you so much right there, Savannah, for pointing this one out. It is a different one. The automatic reader. Automatic reader. Stat 201. An automatic character. Okay. Here we go within the automatic character recognition one. So this one really breaks the same question we did earlier down into multiple parts right here. And when you work this question right here, it's going to be very important to check if you're meeting the conditions. So how do we check to see if we meet the success failure condition? What, and what need to be greater than 10? So we need what? And good to see here, Patrick. For the success failure condition, what do we need to be greater than or equal to 10? And this is what this is going to be checking here shortly. There's a tougher part to this question, which I'll be going over in a moment. But what do we need to check to see if we meet the success failure condition? What, and what need to be greater than or equal to 10? And the important thing to know is that we're working with categorical data here. Does the card reader recognize the character? Does it recognize it, which is a categorical question? Yes, no, it recognizes it this percent of the time. It doesn't recognize it this percent of the time. And I think the true proportion was 83%, according to probably the manufacturers. So we have 83% of the time it recognizes it. So we're going to put the true proportion over here at 83%. And then the percent of the time it doesn't recognize it is this. Remember, does it recognize it? Does it not recognize it? Now, this question gives you a variable sample size, which is part of the issue, where you're doing different n's right here, where the n is going to change between n of 25, 50, 75, and 100. Now, you'll see as you work this question, what we want to check is probably NQ. Now, the reason we need to check NQ is because, and we'll write NQ down here on the bottom, Q is this value right here. The reason we would check NQ is because Q is the smaller one. So we're usually going to have more successes than failures, at least expected successes. So NQ is the one to check, and for all these different sample sizes down here, we're just going to multiply by like n of 25, n of this, n of this, n of this to see the differences. And what's neat is we can just start like adding up. We can go here to 25 times 0.17, 4.25. And you can literally double it right here to 8.5, or just multiply 50 times. So if you're wondering what I did, 50 times 0.17, which is that right there. And then notice that now when we get over to this one, what do you immediately notice here, Jesse? What do you immediately notice about this one right here at this sample size? At that sample size, what is very important about this quantity for that sample size? There's some very important thing to notice right there when you do the mathematics of 75 times 0.17, and that's the key thing to notice. And then the last one right here is going to be 17% of 100 right there. But 75 is a key thing to notice immediately. There's a key thing to notice. At 75, we have what? At a sample size of 75, we have what? Very, very important to notice. We have at least 10 successes, at least 10 failures. So the at least 10 successes, at least 10 failures means we passed the condition. So when we go over here and look at the data, you'll notice this is left skewed. This is kind of left skewed. You might not be able to see. You might be like, does that pass? But checking the success failure condition confirms it does not pass. This is normal, because both of those have at least 10 successes, at least 10 failures. So this passes and this passes. These two do not pass. They do not have at least 10 successes, at least 10 failures. If you wanted to calculate the amount of successes, it would just be here 83. It'd be the complement because you must add up to 100. You could also do the mathematics of NP to get 83% of 100 to find the value down there of 83. So just depends on how much work you want to do to check, but you really technically only have to check the smaller one because you're trying to see if they're both greater than 10. 83% is a much larger percentage right there. So you do want at least 10 successes, at least 10 failures, but checking the smaller one always works. It was technically 20, but 20 is not going to pass and still be left skewed. So skewed to the left, approximately normal. And we answered all of those because we did the work down here on the bottom. Good to see. Maisie's been here a while. So I see the chat move and I'm like, ooh, who's here? So these are all left skewed right here. It would be hard to see a little bit on this one, but remember we did check it. It's not normal yet because it doesn't pass the condition. Now here's we get into the easier question. Let's do the easier one. The range of the first one's 0.5. Just looking at the range from 0.5 to 1 is 0.5. 0.45, or no, it's 0.35. 0.35, 0.20. So 0.5, 0.35, 0.35, 0.20. Okay. So greater than 40, then 0.35, 0.35. If you notice the range is getting smaller, that's because p times q over n square root is getting smaller. And then the last one I think was 20. So not narrow, less than 10. It's between this, relatively narrow. Once again, to find these answers, we're looking at this right here, 0.75 to 0.95. Doesn't quite go to it, but it's definitely not less than 10, so it's not the most narrow. 0.5 to 1 is 0.5. But the harder question on this, which is pretty tricky, and they're very particular about this, is finding out where the center of this bin is. The center of this bin is actually going to contain 0.83, which is the truth. So sometimes you get some easy answers right here where obviously 0.83 is inside of this bin because that's the truth. You get an answer right here where 0.83 is inside of this bin. Pretty obvious right there. You get an answer right here. And it should be, this is where I get worried when it's very close. Technically, it should be, we're going to check that one. Yeah, Moira remembers this one. This one's tough right here with the bins. And then the last one right here, we get very lucky where they put it right here, 0.82 to 0.84. And 0.83, the truth is contained in that bin. But this last one we're going to look at and see if the bin right here, 0.825 to 0.85, is the answer on the third one right here. And you really have to zoom in on it. We'll pop it out so we can look at it. And now you want to start labeling your axes. So what we're looking for, this is the tougher part of this question, is we want to go down here and we want to start marking the axis. Hopefully you can read my handwriting, but I'm trying to go 67.5, 70, 72.5, 75, 77.5, 80, 82.5, 85. And this is the bin right here we're looking at. And that's from 82.5 to 85 because the bin goes up in units of 2.5. So the bin distance right here, and I dropped the decimal because my handwriting is not small enough to do that, it goes from 65 to 67.5, 70 to 77, 72.5. It almost looks like a and 75 to 77.5, 80 to 82.5, 82.5 to 85. And that does confirm the bin we are interested in is from 82.5 to 85. And we did luck out a little bit because theoretically 83 should always be in there. But sometimes your value lands on the edge of one of those bins. This is where you're probably going to lose points. And you might have to look at the graphic and confirm answers. Like this is from 0.5 to 0.6, 0.6 to 0.7, 0.7 to 0.8. Is where the bin is at. Ooh, I miscalculated. 0.5 to 0.6 to 7 to 8, 8 to 9, 0.8 to 0.9. I was like, wait a minute. The bin should be containing the number. So definitely check. A little bit harder of a question. Should get 100. Should get 100. There we go. But relatively good theory. We've talked a lot today so far about how the distribution of the sample proportion gets smaller as n increases. And that can be seen over here. And we also showed it theoretically on this problem that as n increases, you're going to see a smaller standard deviation of the sample proportion. And that is what this question illustrates by the standard deviation getting smaller, but the mean, the center of it stays in the same spot. So the mean is not dependent on the sample size because it's just the true proportion. So since it was in the previous problem 0.83, theoretically speaking, 0.83 should always be in the center of the distribution, which 0.83 is about there, 0.83 is about there, 0.83 is about there, 0.83 is about there. It's just in the middle bin because that's the way the sampling distribution of the sample proportion works. Okay, really good question. And as Moira said, that's a tough one. Do we have any others? So that was the automatic card reader. I think Jesse has another one maybe. Let's see right here. What other ones? For our final project, we did that one. I don't think we did the distribution of test scores. Who did? I forgot already. No, we didn't do it. The distribution of test scores. How many automatic card reader ones are there? Just 2. Ooh, look at that. We got a skewed distribution right here. Yeah, thank you, Savannah, right there. The distribution of test scores. Here we go. We're going to do that one right here. Let's check it out. Stat 201. Here we go. The distribution of scores. And the distribution of scores for a particular test is skewed to the left. The professor wants to predict the maximum score and understand the distribution of the sample maximum. This sounds like a odd question already. She simulates the distribution of the maximum of the test for 39 different tests with a sample size of 5. The histogram to the right shows a simulated sampling distribution of the sample maximum for these tests. Would a normal model be appropriate? Ooh, Terry. Ooh, what have you done? I think we actually need to eliminate this question. I'll explain why here in a second. This question is a quantitative question. And they're going to get at it right here with no. The sampling distribution of the maximum score is skewed to the left, so normal null would not be appropriate. The mean of the distribution is this, and distribution is this. Would you expect 6 grams to have the maximum within 3.5 of 46.8? No, the 68, 95, 99% rule is based on the normal. This question has to be removed. So this question, it's a pretty simple question, but the problem is, so here's a problem with this one, Savannah. This question, which other people might have it, so I leave these in the video. This question is the next chapter. This is not sampling distribution of the sample proportion. This is sampling distribution of the sample mean because the maximum score on the test is a what question. I started to worry as we were reading the question. I was like, where is this going? I think this is a new one for this semester. The maximum score on the test is a what question. The maximum score on the test is a what question. So this is not sampling distribution of the sample proportion. This is sampling distribution of the sample mean because the maximum score on the test is a what question. Like if someone told you the maximum score on the test, they're telling you a what sort of question type, which is what we do right here when we make sure we're doing the right conditions. So this is not the right sort of thing for what this chapter is. So this question should not exist in this chapter. The maximum score on a test is a quantitative question. Like, well, how much was the maximum score? And then you could compare. And so with this, yeah, so that question right there, I'm going to eliminate it right now because it literally should not exist in this. Like there was one we did earlier, the standard error one. It's a very theoretical one. It's like, as I say, sometimes there's questions I like a lot. Sometimes there's questions I'm like, eh. But that was question number 4. That can't be the conditions. Let me double check. It says conditions. What? No. That's why. Here is why, and I'll show you. This is why the error exists. So we can actually be mean to my Pearson right now. You ready? So check this out. It says, question number 4, check conditions for using normal model for sampling distribution of sample proportion. So this is a problem with my Pearson right now. Sometimes I wonder who they have. Once again, my Pearson, a lot of great stuff. A lot of great questions. We've done so many good ones today that really Oh, I know, I'm always mean to them, right? But that literally says right there, check the conditions for using a normal model for the sampling distribution of the sample proportion. And then when you click on it, it's this question right here, just so you know I'm not doing anything funny. And then it's what is the score? And it literally gives you the mean and the standard deviation. That's not the proportion. So this is, once again, an error right here. Every once in a while there are errors. So what we are going to do is we're going to just straight up remove this question. It might remove a question group, which I hate. But that is not a question that we should have right there. So let me go to assignment manager. And we are going to delete whatever questions involve question 4, because that one should not exist. Let's go to, I can replace a question. Okay, let's replace it. Replace question 4. Replace question. Go to the main screen. Just put the easiest question there, right? Well, I'm not on the screen anymore. Oop. Question 4. Sampling distribution models and confidence intervals. No. Here we go. Might get a repeat question now. Okay, good. RA1. Let me double check. I'm putting a multiple choice question right here. Okay. Replace question. Replace. That should do it. That question is replaced now for our class. It's a multiple choice though, so that's easy enough. It's a success failure condition 1. Like I can look at it and be like, oh, multiple choice success failure. Boom. Let's just toss that on here. That's got it. Let's see. What other questions do we have? We'll go a little bit longer here. Got so many things open. It has now been replaced. Oh, can you not replace it? After you replace it, can you not replace it again? Oh, wait, I had to hit done. Oh my gosh. I didn't hit done. I think I've done that before. Like you go replace question, pick question, and then you have to click done. It's like, well, why do you think I'm replacing it? Do you think I'm going to be like, nah, last moment here, I'm going to decide not to replace that question. Like, man, I did all that work of finding a question, replacing it, and then last moment, I'm like, hey, you know what? Maybe I don't want to replace it. Maybe I don't want to. Can we do suppose 30% of your people talk on their cell phone? Yeah, we do. It's a pretty fun one. Let's go do that one again. Like, don't worry. We're finishing up here, but let's do the 30%. So for that one, it all boils down to
notation, brother.
Notation. So get ready to mark that notation. Savannah, thank you so much. 100 points for being here. Keep asking those questions. We want to do as many as we can and review. So with suppose 30% of people, we'll get started here in a second. I'm loading up the questions because I had to exit out of my Pearson. With suppose 30% of people talk on their cell phones, what information is it giving you right now? What information is it giving you right now? It says suppose 30% of people in your town talk on their cell phones. So what information has it given you? What information has it given you? Suppose 30% of people talk on their cell phone. Yeah, Patrick, which one's yours again? Drop it again. We'll do it next. So suppose 30% talk on their cell phone. What has it told you? Oh, please tell me I did not. Okay, good. Oh, that's why. I thought I exited out of my notes and I didn't. Whew. With suppose 30%, I'm loading it up here as we talk. There we go. Got that. Good this. Okay. Here we go. I've only got like 4,000 more characters left. The type description. Boom. Let's do it. Oh, no worries. Well, not a p-value. P-values are probabilities, so it doesn't give you a p-value. Good answers right there. We did. We'll do it again. Have a little fun right here. And good question, Patrick, right there. So p-values are probabilities. So it does give you a probability, but p-values are based on a statistical test. So I actually did some statistical tests earlier over here when we were looking at some jump work. These are p-values because they're probabilities based on a statistical test. So we're not running a statistical test. Let me rephrase this. Are you ready? It is a fact that 30% of people talk on their cell phone while driving. What have I just told you? It is a fact that 30%, like what in notation have I told you? You're very close, Savannah, with your answers. So there's a difference between p-values and another notation we're using. There's a difference between p-values and another notation. But they're both decimals. That might be where some of the confusion is. Be careful, Jesse. So close, 100 points right there. If I say it's a fact, I'm telling you what? If I say it's a fact, I'm telling you what? If I say it is a fact that 30% of people talk on their cell phone. If I'm exclaiming it that way, like it's a fact that 30% of people talk on their cell phone. You might say, well, you're claiming this, but I'm not telling you any sample size relative to it. So if I say it as a fact, or if I say this is true or suppose this is true, I'm not telling you p hat. I'm telling you p. Because I'm saying this is the truth. I'm saying this is the truth, the parameter. Exactly, for the whole population. Moira's got that notation right there. The parameter is for everybody, so we're saying like the true proportion of people who talk on their cell phone is 30%. Once you know p, you should automatically find what? Any problem that tells you p, you should automatically ask for what? A problem tells you p, you should instantaneously say, let me find what? This is the themes you want to get into doing. You say, I know p is equal to this, q, boom. And q is the complement, which is 1 minus, and there's q. Then it says you watch 50 people drive, which is n. So we could model this, and let's think about what this means. I'm going to change the theme of this question a little bit to give it a little more context. I hope you'll watch this second version, because when you solve this, if I told you 30% of people at UT own a dog, and you went out and talked to a bunch of people, what percent of them would you expect to own a dog? So this is the expected percent of your sample, or expected proportion of your sample. 30% of people at UT own a dog. I'm just changing it to own a dog instead of talking on their cell phone. What percent of people, don't even worry about a sample size, would you expect to own a dog? 30% of people own a dog. You talk to a bunch of people, what percent of those people would you expect to own a dog? If 30% of people own a dog, 30%. Great job, Marjorie, right there. That's it. It's like, well, I'd expect to see the truth. So the truth is what you expect to see in a sample. That's the way to read that. That's the expected sample proportion. Now, does that mean if I go out and let's say, and this we'll see a condition problem here, if I talk to one person, is it even possible to see 30% of them owning a dog? See you, Moira. Excellent work. If I talk to one person, is it even possible that 30% of one person could own a dog? Is that even possible? No, it's not even possible. And at that point, we have a problem with the success-failure condition. You can actually see this. I wonder if I still have it open when we model it. So let me go back to the binomial applet and show you the way the distributions kind of look. If you were to only talk to 5 people and expect 30% of them to own a dog, or let's say even just 2 people, it's very skewed to the right. So you'd say I'd expect 0.6 of them. How in the world are we getting 0.6? Like if 30% of people own a dog, and we could go up here to talk to 3 people, and we'd expect about 1 person to own a dog. How is this number down here, the expected value, being calculated? And these are the important things to think about. How is the expected value down there being calculated? So the expected value of 0.9, which would say we'd expect 0.9 people to own a dog out of 3. If 30% of people own a dog, we'd expect basically 1 person, but technically 0.9. So how is that being calculated, the expected amount of people to own a dog with 3 people? It's basically 1 person. Not p divided by p hat, but the expected amount of successes is what? Good guess, Marjorie right there. What is the expected amount of successes? How do we do it right here? We got the notes on the screen. Remember, it's not about solving one problem. It's about understanding the theory. The expected amount of successes. Remember, we have 3 people, right? So check your math on this. If we have 3 people, we're going to talk to 3 people, and we know that 30% of people own a dog. How would you find out the expected amount of people to own a dog? I've got it down there on the bottom third condition. How would you find out the expected amount of people to own a dog? Just 2 letters you got to type. So think about how they got 0.9. How did they get that 0.9? What math was done? To say, well, if we talk to 3 people and 30% of people own a dog, I can make your life way easier. Watch this. Yep, great job, Marjorie, right there. Because imagine if you talk to 100 people, how many of them would you expect to own a dog? If you talk to 100 people, how many of them would you expect to own a dog? 30% of people own a dog, so how many of the 100 people would you expect to own a dog? I haven't hit enter yet, and it'll change the answer at the bottom. 30, right? If you talk to 200 people, how many of them would you expect to own a dog? If you talk to 200 people, how many of them would you expect to own a dog? And think about what you're just doing right here. It's like, well, 30%, there you go, 60 right there. And you can see the answer down there in the bottom, and you can see the normal distribution curve. We can do 50 right here, and we'd expect 15 to own a dog. The very important thing about 15 and 35, which is the other number here, 15 and 35 are both what? And we're checking the condition by doing this. 15 and 35 are both what? So when we do the check on this one, we get, what is the big thing about 15, which is this, and Q is equal to this, and thus NQ is equal to this. What's important about 15 and 35? To be like, okay, good. What's important about it? What is very important about those numbers? They are both what? Very important distinction about 15 and 35. Very important thing, we're like good and good. 15 and 35 are both at least 10 successes, at least 10 failures. And that means we get this normal shape. If we don't have at least 10 successes, at least 10 failures, we don't get the normal shape. So the normal shape is only achieved with random, less than 10% of the population sampled, and then at least 10 successes, at least 10 failures, and we meet the condition here. Now, interestingly enough, you'll notice we actually get a standard deviation right there of 0.324. They do a little bit, they use the binomial for this, but here we are of a standard deviation of about 0.065. Now, how is this calculated? Well, the standard deviation is via the formula P times Q over N square root. P times Q over N square root. So what's going to be important right here? Notation. So let's go ahead. Oops, didn't want to do that. And we're just going to take, we've got P, or else write this. How'd you get 50 again? Right here, sample size of 50. So they say you watch 50 cars go by. So there's our sample of 50. Good question, Savannah. Thank you for asking. Standard deviation of P hat is equal to P times Q over N square root. And then we plug in 0.3 times point that, reverse them. And then we'll do the first one. We'll do P and Q in the right spots. That way people don't get confused. 0.3 times 0.7 over 50. There we go. And then square root. And there it is, 0.065. No worries, yeah. Good work right there. A little tricky, and that's the answer, and we have enough information to solve it. No worries, Savannah. Keep asking questions. That's what I want people to do. You get 100 points for just not worrying about it and asking a question. That's what we do right here. I think we got one more. A philanthropic organization. Patrick, let's do that one here. A philanthropic organization. What are these philanthropy organizations doing? Is this the one right here? Looked similar to what you asked. Might do that one. What? Wait. Replace that. Oh no, am I in the other? Oh no, did I have to replace it in both sections? Oh my gosh. I got 2 sections. We did it in the video, and it's a multiple choice quick one, so it has a table with it. This, not this one, right? I swear they're trying to trick me here. It starts out, the very start of it again, Patrick, is, and is this chapter 13 quiz or chapter 13 homework? Chapter 13 quiz or chapter 13 homework? Pearson's. I think Matt Pearson's mad at me right now. Oh, the homework, that's why. We'll replace the question if you already started the quiz. It doesn't replace. I think you have to restart the quiz. Do the two complete sentences. Which one's the two complete sentences, Savannah? Can you repost that one again real quick? The homework. Let me go to the homework here. Matt Pearson. As the sample size increases, oh yeah. Awesome. Thank you, Jesse, right there. Oh, those right there, yeah. Remind me 4 and 5 after this. All right, here we go. Got a table right there. Got it. A philanthropic organization. This is one of those theoretical ones again. What do you think we need to do immediately when starting this question? Work on this with me right here. What do you think we need to do immediately when starting questions like this? What do you think we need to do? Remember this when you get to the test and know it really well because it's going to be the key to a lot of test 2 problems. Write the notation.
Notation, brother.
So they already tell us some of the notation right here. The true proportion is equal to 0.07. And then they show us different sample sizes right here. They have the observed and theoretical mean. And that is because, and if we write down our notation on this, well, the theoretical mean is going to be, and this will actually answer those questions you're wondering about, Jesse. So look at how this works and then remember those answers to the next one, is mu p hat equals p. And if p is equal to this, all the theoretical means will be equal to 0.07 because mu p hat is equal to p and p doesn't change. So all of these are mu p hats right here and they're just the same. So take a look at this right here. As the sample size increases, what happens? So this is the sample size increasing right here. What happens to the standard deviation? So as the sample size increases, what happens to the standard deviation? And you can look here mathematically at it. So as the sample size increases, what happens to the standard deviation? It gets smaller. Yep. And you can see it up there. And you can also understand that you're dividing by n. So as n gets bigger, the standard deviation gets smaller. So this also shows it. And then we can see here theoretically with the histograms that the histograms have less variation. Look at how this one goes from 0 to 0.25 and is for the smaller sample size. This one goes has a sample size of 200 and only goes from 0 to 0.15. And this one has a little bit of a right skew still. What was the 0.7? 0.07 rather. So looking at the histograms, what is the smallest sample size at which the researcher can be comfortable using the normal model? What do you think we should check to see if we should be using the normal model? So what do you think we should check to see, because they should randomly sample, they should sample less than 10% of the population, and we should meet the success failure condition. Where do you think the problem is going to be where it won't be nearly normal? Or we should just say normal. Don't want to confuse conditions. Where do you think we should check? Which one of these do you think is going to be the issue for us? Did they randomly sample? Well, that would apply to all of them. Did they sample less than 10%? So hopefully they don't have too small of a population. And then success failure. So where do you think is going to be the stumbling block? Where do you think the issue will be? I would say it's going to be on the success failure. So how would we check this for the sample size of 100? For a sample size of 100, how many expected successes would there be? Number 3, you got it right, Jesse. So number 3, or with the third condition, success failure, with a 7% success rate, how many successes would you expect? So with 7% expected successes, how many successes would there be expected? 7. Great job, Patrick. Are there 100 points? And Jesse, 100 points too. So do we pass it at 100? No. How many expected successes would there be at 200? How many expected successes would there be at 200? Exactly. So we have at least 10 expected successes. So that would be it right there. We pass with that. What does the success failure condition say about the choice made in part A? We have at least 10 expected successes and at least 10 expected failures. They are both at least 10, so it is met. It's right there. Oh, that's good. It's a good question. But just checking the expected successes and expected failures, they give you a lot of information right there, but that's the only key part of it. I think we have the sentence ones right. So complete the sentence. Let's check out complete the sentence. Step 201, chapter 13, homework. Complete the statement below. You're welcome, Patrick. Great work right there. Did I click something in the video? I don't think that matters. There we go. All right, good. I almost changed it to a different thing. As the sample size increases, the mean of the sampling distribution does what? What happens to the mean of the sampling distribution as sample size increases? What happens? Don't read their answers. What happens to the mean of the sampling distribution? And it stays the same. Exactly. Because it's always what for this instance? The sampling distribution of p hat always has a mean of what? What is the mean? It's always equal to what? It's always going to be equal to what? And there's the notation for it right there. It's always going to be equal to P. So if I tell you something like 51% of people are women in the United States and you sample 1,000 people, be very careful in answering this. What proportion would you expect to be women? So the key question is, what proportion would you expect to be women? So in your sample, what is the expected sample proportion? Be very careful. We're asking proportion, though. That's key to this. Think about proportions have rules that they're between 0 and 1. So what is the expected proportion of this? So if we sample 1,000 people and we know 51% of the United States is women, what proportion would you expect to be women in your sample? So this is expected sample proportion. So what is your expected sample proportion? Boom. That's just it. That's the proportion you'd expect. Has it changed now, Jesse? Yes or no, has it changed? Has your expected sample proportion changed? And I'm not saying how many you expect to see. I'm saying the expected sample proportion. No, it's still just because it's just P. It's whatever that is right there. So if you change the sample size, it's still just the same. But look at this right here. The sample size is going to change the standard deviation. As sample size increases, standard deviation is going to get smaller. So this will do nothing to it. It's going to stay the same right there. And then the other one, as sample size increases, the standard deviation gets smaller. And that's because you're dividing by the square root of n. And just looking at the formula right here. And we had a lot of good theory ones too. So take a look at the theory ones where they even show you how this works. Where was the problem we did with the table? Because that literally shows you as part of the problem the mathematics of it. And you can see here the standard deviation getting smaller as sample size increases and the mean stays the same. Now, these are the theoretical values. This is what you see in a simulation, and the simulation pretty much matches the theoretical values. Well, I'm going to take a short break, grab some lunch, and then we'll be teaching class. So great work, everybody. Jesse, amazing work, amazing questions. We did a whole lot today. Look at all this right here. Woo! Wow, a lot of chapter 13. So we're going to take a quick break right here, come back after some lunch. Oh my gosh, I almost clicked close on OBS. But with that, bye for now, everyone. Bye!